Let's talk about the angular momentum of systems of particles. Here I have a system right here, and we will calculate the angular momentum of this system. The first thing we have to do is choose a reference point, because angular momentum is r cross p, where r is defined relative to the reference point. It is the position vector of the particle relative to the reference point. As a tip here, usually it is useful to place the origin of your coordinate system on the reference point also. You don't have to, but it is usually convenient to do so. So there we go. I've drawn my reference point for calculating angular momentum of this system of particles in red right there. I will calculate the angular momentum of the system of particles about or relative to this reference point. I could have chosen any reference point to calculate the angular momentum of the system. I would have gotten a different answer. It would have also been valid, though it would have been different. But this is the reference point about which I wish to calculate the angular momentum in this example. The next thing to do is to calculate the angular momentum of each individual particle with respect to that reference point. All of those are added up together, and that creates the total angular momentum of the system. I have drawn in blue the position vectors of the particles with respect to the reference point. I have drawn in green the momentum vectors of each of these particles. I can then perform the cross product for each particle. For example, this particle, I can take its position vector in blue and take the cross product of its momentum vector in green and get the angular momentum for that particle. I then add up all the angular momentum of each individual particle, as I already stated, and there we go. That's the total angular momentum of the system. We're done. Let's now consider a special sort of system of particles where the particles rotate about the axis as though they were one object. That is, they are a rigid body. For example, there might be thin rods with negligible mass, as I have shown right here. A nice thin rod, which we can neglect because it has negligible mass. And they're rotating together as one object with an angular velocity omega. And as they rotate about a common axis of rotation, which I have labeled in red, which will also be the reference point for calculating the angular momentum of this system of particles. If this is done, as will be shown in more detail in another video, the result is as follows. Angular momentum is equal to I omega, where I is equal to the sum of mr squared, and omega is the angular velocity about the rotation axis. I is a special quantity called moment of inertia, sometimes also called rotational inertia, both equivalent words for the same thing. And moment of inertia is also defined about an axis of rotation. So this I here is the moment of inertia about the rotation axis. Each mass has its own mass, mi, and r is the perpendicular distance from the rotation axis to the mass of interest. We then take mr squared, add them all up, and there's moment of inertia. Multiply by angular velocity, and there is angular momentum for a rigid body. Let me explain this perpendicular distance thing a little bit. Here's my rigid rod example again of two masses rotating about, but now viewed from the side. So the masses are going into the page, rotating around the back, and then coming out of the page and rotating around the front. And here is the axis of rotation. The axis of rotation is in red now, just to indicate where it is at. And these green vectors are to represent the momentum of the particles, which strictly speaking are going into and out of the page, but I tried to draw it in 3D a bit. By perpendicular distance from the axis of rotation is meant this distance, that blue line right there, or this distance, that blue line right there. Those blue lines are perpendicular to the axis of rotation. They are a line that is perpendicular to the axis of rotation drawn from the axis to the masses. That is the distance Ri that goes into the formula for calculating moment of inertia. By contrast, you would not find this distance. See how it is at a slant with respect to the axis of rotation? I am measuring about a point on this axis that is raised above these points, and I'm just drawing a blue line from that point all the way down to these masses. That is not the perpendicular distance to the axis of rotation, and therefore that will create the wrong distance. Nevertheless, notice that its component that is perpendicular to the axis of rotation is still the Ri that we are interested in, the perpendicular distance to the axis of rotation. Now getting back to this moment of inertia and what it is, I will talk about it more in another video, but for now, a few brief points, or perhaps reminders. The moment of inertia is the rotational analog of mass. It quantifies how much resistance an object has to rotation. Or another way to put it, it quantifies how difficult it is to make an object rotate with a torque. So if you have a given torque, if you have bigger moment of inertia, the more difficult it is to rotate. And if you have smaller moment of inertia, it is easier to rotate. Just like with mass and with force, the bigger a mass is for a given force, the harder it is to make it accelerate, to change its motion. Whereas the smaller the mass is, again, for a given force, it is easier to accelerate, to change its motion, its translational motion. Another useful fact about moment of inertia, just like mass, it is additive. So if you want the total moment of inertia of an object, just add up the individual moments of inertia of each part of the object, and then you will have the total moment of inertia for the object. And then, as seen from the definition that we derived earlier, the moment of inertia for a single point particle is mr squared, where m is its mass and r is its perpendicular distance from the axis through the reference point. And as can be seen from the sum that we derived earlier for the moment of inertia of a system of particles, the moment of inertia for a single point particle is just mr squared, where m is its mass and r is its perpendicular distance from the axis of rotation. As with moment of inertia, I will give more detail on this formula, L equals I omega, in another video, but for now, note a few things. Firstly, L, I, and omega, angular momentum, moment of inertia, and angular velocity are all calculated about the same rotation axis. Next, this equation, L equals I omega, does not apply in general, even to rigid bodies. It only applies if you calculate about a symmetry axis through the center of mass that is fixed in direction, so its direction is not changing, or if you calculate about a fixed axis that is parallel to that symmetry axis through another point, or if you're calculating about a fixed axis through another point that is parallel to that symmetry axis, or if you're calculating about a fixed axis through another point that is parallel to that symmetry axis. By fixed axis in that last point there, I mean one that is neither moving nor changing direction, has no translational or rotational motion. It is just fixed still. And it is fixed still relative to the system of particles, the rigid body, and relative to some inertial frame of reference. One result of the axis being fixed is that all points on the axis have zero velocity. You might notice, though, that there was a different condition for the axis if it was through the center of mass. If it was through the center of mass, it only has to be fixed in direction. The axis may move translationally, but it must not change direction. So the center of mass could be accelerating, and you could still use L equals I omega in an appropriate reference frame that I will discuss in another video, but the axis must not change direction. All right, let's see a quick example of using this L equals I omega formula and see how it results in the same thing as R cross P. Let's consider the following example. Suppose we have two particles of mass m1 and m2, and they are rotating together in a circle as one object because they are connected by a light rod of negligible mass. They rotate about the axis of rotation shown in red, and I will have the z-axis come out of the page. What is the angular momentum of this system? We will calculate it two ways to show that the L equals I omega and R cross P formula gives the same result when dealing with systems of point particles. So first, let's calculate using L equals I omega. Omega is basic enough. It is just some magnitude omega times k hat, because the rotation is counterclockwise and therefore the angular velocity is coming out of the page. The k hat, the positive z direction. Next, we need the total moment of inertia of this system. To get that, we should get the moment of inertia of each individual particle first, and then we can add them up. Let's consider the particle at the top right here, the mass m1. Because the two particles are moving in a circle, it is located at a distance big R, the radius of the circle, away from the axis of rotation in red. Its mass is m1, so the moment of inertia for this single point particle is m1 r squared. Meanwhile, for the same reason, we can see that the moment of inertia of the particle on the bottom of mass m2 is, and therefore, the total moment of inertia of the system is just their sum, which of course I can simplify a little bit. The angular momentum of the system then is the total moment of inertia of the system times omega. And there we have it. Let's now calculate the angular momentum of the system using the r cross p formula. And the total angular momentum of the system will just be the sum of the angular momentum of each particle. Let's look at the particle with mass 1. We see that its angular momentum is r cross p. We can clearly see that p, m1v, is perpendicular to the radius vector, the position vector r. So the cross product, its magnitude, reduces to just the product of the magnitudes of the r vector and the momentum vector. The momentum of mass m1 is m1v, as said before. And so we get as follows for the magnitude. As for the direction, we need the right-hand rule. So just imagine translating this p vector downward, so that way the momentum and the position vector are both coming from the same origin. And then we can do the right-hand rule. Put your hand in the direction of r, curl in the direction of p, and then your thumb should be sticking out of the page. And so the angular momentum is coming out of the page. It is going in the k-hat direction, the positive z direction. Similarly, you can calculate L2, and you will find from the same process of reasoning that we get the following. The position vector to mass m2 is perpendicular to the momentum vector, so the magnitude is just r times the magnitude of p, which is m2v, and so you get big R m2v. And then the direction by the right-hand rule is also in the positive k-hat direction. Now, notice for the next step that the velocities of the particles in the system are the same. They both have velocity v. This is because they are connected by a light negligible rod. They are rotating together as one object. They are going to have the same velocity. Because we want to be able to compare our result here with our earlier result, we should change these velocities into omega. Omega is the same for both of them as well, because they are rotating as one object with one angular velocity omega about the axis of rotation. And so, for example, L1 becomes as follows with this omega r, which then simplifies into m1 r squared omega k hat. For the same reason, L2 will transform into m2 r squared omega k hat after plugging in v equals omega r into the formula. The total angular momentum of the system then is m1 r squared omega k hat plus m2 r squared omega k hat, which simplifies to the same result as we had earlier, pulling out the common factor of omega r squared and the k hat. And there we have it. We have the same result for a system of point particles, although it was a lot easier calculating it by the I omega formula. Now you might ask, what if the rod's mass was not negligible? Well, then you would just find the moment of inertia of a rod about this axis of rotation, which is at its center of mass. So you'll find the moment of inertia of a rod about its center of mass, and then you would add it to the total moment of inertia. You would still multiply by omega, the angular velocity of the system, because the angular momentum of the system is the total moment of inertia times omega, and omega isn't going to change whether you include the rod or not. So that's how you would do it. Of course, a rod is not a point particle, so now the angular momentum calculation differs from the r cross p way of doing things. The rod is inherently an extended, rigid object, and we can't just apply r cross p to it in a naive way. But I will talk about this more and the relationship between these equations and when you can use them in other videos.